So now that I've presented you with all of the relevant theory on conformational analysis, I think I'd like to spend a few minutes just solving as many problems as we can. A lot of these are going to come from certain PowerPoints within the lecture notes that I've already posted. Some of them I'll use other sources. And I'd like to have an emphasis on just simplifying things as much as possible. So if you look at slide 53 with me, have a fairly intimidating problem, and we want to be able to name the molecule, to draw the bond line structure, and then draw the Newman projection that shows the highest energy conformation. Let's tackle these one at a time. So our first step will be go ahead and open a new one. And I'm just going to draw the same Newman projection that were provided on slide 53. Now they're kind of taking it easy on us because they're not asking us to do stereochemistry. That's something that we'll see very soon. So we have two carbons, and we were looking down the axis of this sigma bond. So I think that would be a very good place for us to start. Carbon in the front, carbon in the back. Now the carbon in the front has a methyl group and is also bonded to a cyclopropane ring. And it makes two bonds, a cyclopentane ring, and it makes two bonds with that cyclopentane. Carbon on the back, we have two ethyl groups, and of course we have a hydrogen. In terms of the longest chain, I think there are a couple ways that we could do this. First, let's try to find our longest continuous carbon chain. 1, 2, 3, 4, 5 is one way that we could go. We could also name this as a cyclopentyl group or as a cyclopentane. And I think that the latter is probably the better choice. So let's go cyclopentane. And of course we'll want to call this carbon 1. And so we're going to have 1 methyl. Now with this group, we have a 1, 2, 3 carbon chain as the longest chain. So that's a propyl, but there's an ethyl group off of carbon 1. So we would want to put this in parentheses, and I'm going to place it down here. 1 ethyl propyl. Cyclopentane. Again, 1 methyl, 1 ethyl propyl, cyclopentane. This answers the first question. This is an appropriate bond line structure that we've drawn, by the way. We can improve upon it. So here's the cyclopentane portion. Here's the 1 methyl. And then we have 1, 2, 3, and off of 1 we have an ethyl group. 1 methyl, 1 ethyl propyl cyclopentane. And last but not least, let's look at drawing the most stable, or excuse me, the least stable conformer, which is going to have the cyclopropyl ring, the cyclopentyl ring, and the methyl groups eclipsed. So I'm going to place this one in red. And I'm just going to keep the front carbon steady on this one. And if you use just a little bit of logic, you should realize fairly quickly that when the ethyl groups eclipse the cyclopentyl ring, it's going to be most unstable. So this would be the highest energy conformer. Highest energy conformer. And that answers all 3 phases of this question on slide number 53. Let's move on to another one. This one's a bit more interesting because now we have a trisubstituted cyclohexane ring where we have 1-T-butyl, 2,5-dimethyl cyclohexane. So this one's just a degree more difficult than previous ones that we have seen. So let's first draw this in the planar conformation. And of course we want to draw the chair conformations next. And honestly, it doesn't make any sense to even draw the conformation that has the T-butyl group in the axial conformation. Again, I want to emphasize the plane. I think when we do that, it's a little bit easier to see what should be north and south. So I'm going to place this T-butyl group equatorial. And then our methyl group needs to be going cis. Again, let's remember that this is north, this is south. We know that the T-butyl group is going to control the conformation of this molecule. And then, of course, we have another methyl group that is cis to both the T-butyl group and the methyl group. And of course, this is going to have to be equatorial as well. Now there's no controversy. By the way, it would be better to have the T-butyl group equatorial and both methyl groups axial. But here it's a home run. This is clearly the most stable conformation. Now, the highest energy conformation is going to be the chair flip. Again, I want to emphasize the plane. I feel like the little midget guy on Fantasy Island. The plane, you got to draw the axial and equatorial. You guys are too young to remember that, but that's some funny shit there. Okay, so T-butyl group. Again, if we call this carbon 1, 2, 3, 4, 5, and 6. Carbon 1, 2, 3, 4, 5, and 6. So the T-butyl group is on carbon 1. Methyl group on carbon 2. And methyl group on carbon 5. And this would be the highest energy conformer. Whereas the one in orange is the lowest energy conformer. This is a great exam question. Permutations of this are the kinds of problems that I like to ask on exams. So make sure that you feel comfortable in doing problems like this. Okay, now let's go back a little bit further and do some easier problems. And I'll give you guys what you want, your little black canvas color. Now everybody can be happy. I'm going to draw 2 molecules . And the question is, determine whether the following pair are constitutional isomers, identical, or no relationship. My solution to this is going to be real simple. Let's shade in the longest chain. Actually, we'll just kind of lasso it like we did in class. And I'm going to have 1, 2, 3, 4, 5, 6, 7. I'm going to lasso this one as well. You could also try to rotate all these bonds to get them to superimpose, but I think it's easier to name it. 1, 2, 3, 4, 5, 6, 7. This is going to be 2, 5, dimethyl heptane. This is also going to be 2, 5, dimethyl heptane. So these are identical molecules. While we're on this subject of naming and doing some things we should already be able to do, let's take, I'm I'm not sure what page this is on in your PowerPoint notes, but these are things that we should be able to do. So I think this is just good old-fashioned practice. The way I'd like to see class go on Wednesday is for us to do a whole bunch of problems, to go through the theory relatively quickly. And if you guys do the right job in preparing, like watching these videos and tell me what you understand and don't understand, this should not be very difficult to do. So we are given this molecule and we want to name it. So we need to lasso the longest chain. I would say probably the longest chain is going to be right here. And if we number this, probably 1, 2, 3, 4, 5, 6, 7, 8. Let's take a moment to see if there's a better one to draw. I think 8's good. So let's go with an octane. And what are our substituents? We have 3 ethyl, 4 isopropyl, 3 methyl octane. A little bit more difficult than some we've done recently in class, but again, I expect that you guys are able to handle a problem like this. We can also look at being given a name and then drawing the molecule. So 1, 2, 6, 7, tetra, bromo, 4, 1, 2, dichloro, ethyl, no name. Quite simply, I'd start backwards and work my way forwards. There's 9 carbons off of carbon 1 and 2 and 6 and 7. I have bromine atoms. And off of carbon 4, I have an ethyl group that has 2 chlorines. At 1 and at 2. And I have successfully drawn this molecule. Now let me give you a couple problems to think about. Again, if you all will remind me, we can work on these in class. Draw the lowest energy conformation of the following. Also be able to name these. Again, I can almost guarantee you that on your next exam, you'll have a problem very similar to this. Which of these two are more stable and why? Drawing all chair conformations and using sound principles of conformational analysis in your argument. So let's save this for an in-class activity. And so I am going to stop here, and next lesson I will podcast will be on acid and base theory, which I hope that we cover very shortly. And that is the reference chapter for that is chapter 3.